Okay? All right. Next example in the script, we have 50 liters of oxygen at STP, and I want to know how many moles and how many grams of water I'm going to get out of it. Another way of writing it is I'm going to solve for moles and take that answer and convert it over to grams for water. But the key here is now at STP, because if I'm going to convert liters to moles, I have to have some kind of correlation between them. It isn't like the previous problem, you went from liters to liters, you're not changing the moles at all, you don't care what the conditions are, it stays the same. This does depend upon the conditions. And again, we're using the same equation that we used before, so we can keep referring back to it. So, let's take this first problem we have written down here as an interpretation of what we have up there. We have 50.0 liters of oxygen times fraction length. And I want to change liters of oxygen over to moles of water. The problem here is that I'm converting two things in the label. Liters to moles, and then oxygen to water. I can only change one part of the label in each step. So I can either change liters of oxygen to moles of oxygen, or I can change liters of oxygen to liters of H2O. I believe on the script, I don't have it in front of me, I think I would change liters of oxygen to liters of H2O. That requires nothing extra. So I'm going to put liters of oxygen on the bottom, and I'm going to change the liters of H2O on top. The liters stay the same, but the substance of the label changes. And that'll cancel out the liters of oxygen, gives me liters of water. Then I'm going to change liters of water to moles of water. In this case, the water stays the same, but now the label itself in front of the substance changes. So there's one change in that entire label right there for each one. So now, here's what the question comes. And I'm going to do both examples of this so you can see how it would have been different had I taken a different track. Okay, so liters of oxygen, liters of water. This is going to come from the stoichiometry of the equation. So we take a look, liters of oxygen, there's a 5 coefficient in front of the oxygen. The water, there's a 4 coefficient in front of the oxygen. So when you're going from volumes of gas to volumes of gas, you're using the stoichiometry. Now, moles to liters, this is where the STP part comes into play. When we were talking about how we can change over moles to liters, I used STP as an example. And I said that 1 mole of a gas, no matter what the gas is, has a volume of 22.4 liters. That is a number you should keep in mind when you go through these, when you're dealing with STP. So, that means for every 1 mole, it's going to be 22.4 liters. This number will always be 1 when you're changing over to liters. It's like using the periodic chart. You'd only use 1 mole for a periodic change to grams. This is going from liters to liters. That is using the chemical equation. This is like going from moles to moles, which I'll show you just a little bit. In fact, I'll do that right now. Let's do it the other way. I'll come to the answer just a little bit here. So let's again take 50.0 liters of oxygen times, and again, we're just going to do the labels. Put liters of oxygen on the bottom, only this time we're going to change that to moles of oxygen. So the liters of oxygen cancel out, now I have moles of oxygen. And then I'm going to go from moles of oxygen to moles of H2O. In each case, I changed one thing. I changed the measurement here, but I left the substance alone. Here, the measurement stays the same, and I'm changing the substance. Only one change for each fraction. All right? Now, the number of liters in a mole, that is what STP volume is defined as 22.4 liters in a mole. So I put the 22.4 liters right here, and 1 mole right there. And when I go from moles to moles, again, the equation refers to molecules, moles, and volumes of gas. Well, this is the moles. And when you go moles and moles, use the coefficients in front of the water, which is 5, and in front of the water is 4. And you can see, even though the order is different, it's the same values multiplying and dividing. And no matter which one you use, you're going to get 1.79 moles of steam. But we haven't finished the problem. It says moles and grams. So either one of these is going to give you this value right here. And the next one is just a use of the periodic chart. 1.79 moles of water times fraction line moles of water on the bottom of the periodic chart. And although we've done this like a bajillion times, we're going to change the grams of water. Again, water stays the same, but you're changing the label from moles to grams. And 1 mole off the periodic chart will give you 18.0 grams. And when you multiply this out, you're going to get 32.2 grams of voila. Okay, so the nice thing about this process is that there is more than one way of doing this. So you get to pick whatever your personality prefers. It's a deep psychological process. Now this gets a tad bit on the ugly side. So we are going to change grams of carbon dioxide over to liters of oxygen at 25 degrees Celsius in 1 atmosphere. So we need to find out what the conversion is. This is asking for 1 mole of gas is equal to how many liters at these conditions, 25 degrees Celsius in 1 atmosphere. So this first becomes a Pufner problem. PV equals nRT. Pressure is 1 atmosphere. V is 1 atm times V, are unknown. This is 1 mole. N is 1 mole. R is 0.0821 liter atmospheres over mole Kelvin. And then the temperature is 25 degrees Celsius, which makes that 298 K. And then I divide by the 1 atmosphere, and I get 24.5 liters per mole at atmosphere. At 1 atmosphere, 25 degrees Celsius. So change in the temperature increased the volume by 2.3 liters from the 22.4 to the 24.5. 22.4 at STP. We call these standard conditions. So a lot of times you'll see that used instead of STP for those types of problems. Nobody works in a lab at 0 degrees. No one that I know, unless they're stationed up in the North Pole. So now we can solve the problem. So this is our problem right here. 16.4 grams of carbon dioxide. We cannot use grams in any context here, so we have to change it over to moles. So we'll put grams of CO2 on the bottom, moles of CO2 on top. We get that off the periodic chart. We'll do that after we get the labels done. Grams of CO2 are gone. Moles of CO2 then has to be changed. And this gives us an opportunity to go in one of 2 directions, because we want to end up with liters of oxygen. That is, wow, that's weird. CO2, so what happens when I don't look when I write. So we can change that to moles of oxygen, or we can change that to liters of carbon dioxide. I'm going to change the liters of carbon dioxide. And then my liters of carbon dioxide can be now changed to what I want is liters of oxygen. Okay, so we go to the periodic chart, and most of you have done this a few times. You might remember this is 44.0, but if not, use the periodic chart. But this is only one. This is not coming from the equation. This is coming from the fact that you use the periodic chart, and anytime you use the periodic chart, you are dealing with 1 mole at a time. Okay, now the relationship between liters and moles is what we just did up here. under these conditions, using PubNet, we found that for 1 mole, it was 24.5 liters. So 1 mole is 24.5 liters. Then the liters of liters comes from the equation that we have seen like a bajillion times in this lesson alone. And we know that there's 5 liters of oxygen and 3 liters of carbon dioxide. So we multiply and divide all that nonsense out, and we get an answer of 15.2 liters of oxygen. Okay? So, let's take a look at the practice problems. And we have a frozen board. That's just wonderful. Come on back here. It's okay. I can't wait for my retirement when I take this out to the cornfield and just beat it to death. All right, those are your 5 problems. Have fun.